model is a very common word, but what modeling in engineering or in science-based domains refers to, and we are going to be touching upon that as well. Then the fifth one is introduction to robot operating system. Now here at Cretus and at everywhere at various IITs and even in there are some commercial companies that use robot operating system or ROS. And if you come from a computer science background, you would have some app frameworks like Flutter and web frameworks, Angular. So this is the one for robot. There might be a few, there are other ones as well, but robot ROS is by far the most popular, has wide community support, and allows us to at least prototype our robot very quickly. And obviously, in order to participate, in order to do projects with us, or in order to participate in various inter college competitions, even intra college competitions, ROS is must. So I will be touching upon that, and our the hands-on coding part we are also going to do that in ROS as well. And one minor section is useful Linux commands. We are only going to be touching upon three commands that we are going to use. We are not going to make it complex because there are already a lot of things, and the workshop would get extremely overwhelming afterwards. So this is something we are going to be doing. And then the last section is the hands-on modeling and coding of a differential drive robot. This is actually what the workshop is for. Here I have mentioned a website called Construct. Here it has Linux virtual machines. We are going to be firing up one of those, and then we are going to write the code for it. We are going to simulate. We are going to like move it around. We're going to have lots of fun doing that. So I suggest you get ready. Now, one other important announcement. Uh, we are actually working on the process of creating a team creators from which we are going to be participating in various inter-college competitions like Robocon. So in order to be able to keep pace with the members, these things are a must. So if you are from PDU or any other colleges and you want to get into your respective teams, I suggest you pay quite good attention to this workshop because it will cover up a lot of basics, and you would be brought to speed quite quickly. So let's get started right away. So first, what actually is a robot? And here I would request anyone from the audience to just kind of mention. Obviously, I'm going to tell you the one, and there is nothing right and there is nothing wrong because it's a wide array, or it's a wide field, and there are lots of different types of robots. There are lots of classifications. I might not know one you are familiar with, but I would love to know what are your thoughts on this. So anyone would like to venture a guess? It doesn't have to be accurate or anything. I just want to get the ball rolling. I just want to make sure you are actually there. So anyone? Anyone from the attendees would like to venture a guess?
Anyone would like to tell what a robot is, even in layman terms?
Yeah, because that's the whole point of the workshop. We are going to transform from a layman to someone who can actually read a few research papers and kind of know what's going on. So, yeah, it would be great if you could speak out. Anything. It doesn't have to be accurate, it doesn't have to be true, it just has to be something. Okay, so I guess that's a no. Then I move
Yeah,
forward.
Aniket has raised a hand.
Yeah, Niket, go ahead.
Yeah, a robot is a machine that follows some specific commands given to it to perform a specific task.
Perfect, perfect. Niket, can you please introduce yourself? Where you're from?
Yeah, hello everyone. My name is Aniket Rohara. I am from LD College of Engineering, EC branch, second year.
Thanks, Aniket, for the answer, and thank you for attending. So now Aniket was partially correct. I'll just try to complete his definition. and I'll be building upon on top of that. So a robot can be precisely defined as a set of links that are connected with each other via joints and which are required to move together in such a way to achieve a desired end state. Now the presentation is on, now the definition is on your screen, and I would like you to read it for a minute and try to absorb what it means. Now there are a lot of keywords in there, set of links, joins, end state, and desired end state. So uh, I'll show you one diagram and it will clear some of your doubts. So suppose this is a joint link diagram of a robot. You can see, is my cursor visible, Iria?
Yeah.
Okay. Uh, so as you can see that the one that are given in the curly braces are actually the frames, but you can refer them as a joint number. That is, this is the first joint, second J1, J2, J3, and J4. So these are all joints, and this is L1, which is a link, link 2, link 3, and this all are connected with each other via set of joints. So if suppose I'm instructed that I need to bring this robot in an upright position, that is 90 degrees, like a complete straight line, then what would be the set of thetas, that is theta 1, theta 2, theta 3, and phi, that my robot or this that my robot makes a straight line, or in other terms this xy reaches here. So that is actually a robot forward an inverse kinematics problem. We are not going to be discussing the details of it, but I'm just throwing around a few keywords that if you are interested, you can look up for. So this is actually what we are a robot is. Like we want to control theta 1, theta 2, theta 3, so that our robot achieves the desired end state. That is it. Now, this is a very general but yet a complete definition because that applies to this is a robotic arm. I'm sure you must have seen it somewhere. You if you are visiting any factory, not India, obviously. The penetration is not that much, but it's quite common to see a robotic arm, and even and other definition is a wheeled mobile robot where we have a chassis and we have two or four wheels connected, and like you can imagine a car, but car is also an example of actually an Ackermann drive, and I'll touch that upon later. So the end state can be required joint positions, velocities, forces, or torques, or whichever variable the end user wishes to control. So basically, sometimes depending on our application, we are required to control a few things. We either want to control the position, like where the XY is supposed to be, or we either want to control the velocity, like how fast or slow XY is supposed to travel here or there, or we all can also control what will be the torque of individual joints so that XY gets a certain torque. Now this all depends upon the application. Like suppose for example, in industrial robotics, if you want a robot to move from here to there, then that is an example of position control. But if we suppose if we are I'll give you one example of medicinal robotics as well. If you might have heard about, there is a very common thing called hair transplant. Anyone who has heard that? It's very common. Like I, so robotics in Germany, they have developed this product that the robot maps the coordinates autonomously and then pierces the skin and inserts that nodes or I don't remember the exact term, but then it's an example of force control that we require certain degree of force in order to penetrate the skin. So that is an example of force. First, there is a position control. Obviously, a robot reaches a particular position, and then from that, it is required to control the force. So that is an example of position control as well. Then, based on the application and required degrees of freedom, the types of joints are selected as well. Now, here the keyword is degrees of freedom. Now, I'll not elaborate upon this term degrees of freedom because it's a different mechanical engineering lecture as well. The only I would just define it in a very short and layman way that the number of directions the robot is allowed to move. That's the degrees of freedom. Normally, we have six, like there is x, y, and z axis, and then rotation about all of these axes. So total we have 6 degrees of freedom, and out of that, how many degrees of freedom is the robot allowed to move? That is the degrees of freedom of that particular robot. It's not that simple, but helps you get started. Now I'll just elaborate briefly upon what are the types of those joints. So we can classify these joints depending upon the requirements or of the degrees of freedom of motion that the joint is expected to perform. Like I said, different applications require different types of joints. Sometimes all you need to do is have a pick and place robot. So there will be just one straight joint that goes down, picks it up, rotates, and then drops it again. So that is one application. You can imagine n number of scenarios. But now I'll like to bring you to the exactly the technical terms that are industrial oriented. So the types of joints are revolute, prismatic, cylindrical, helical, spherical, and universal joint. You can see in the diagrams. This is the revolute joint where there is one axis and two joints are just moving, and there is a prismatic joint. This is a prismatic joint here. It's just it's just translating. So this is called a translating joint as well. And this is called a rotating joint. Now these are some other types of joints: helical, cylindrical, universal, and spherical. Spherical provides the highest degrees of freedom, and it is used somewhere it's used extensively. But the most commonly used joints are just revolute and prismatic. But for our application, that is, we are going to be making a wheeled mobile robot, we will require a revolute joint. But we will not refer to, but in URDF, that revolute joint is referred to as a continuous joint because revolute joint has certain constraints. It can only move to a certain theta. uh, it has its own limit in technical terms, but obviously in our wheeled mobile robot we have wheels, and there is an infinite wheels can move infinite theta, right? So that since there are no constraints on the movements of the wheels, at least in terms of theta or in terms of displacement, we can name the revolute joint to be continuous joint, and we'll be fine with that as well. So now a brief introduction to the classification. Robots are classified based on so many factors, so many factors. It is first classified in base of application, depending on upon the application, right? It's either defense or telemedicine or logistics. You can name several industries, and it is classified on those principles. It is also classified on the basis of degrees of freedom, like how many or the types of the joints present in the robot. What we saw here is a 4R robot. That is, there are four revolute joints. It can be a combination of a lot of joints. There can be two revolute, one prismatic, all three prismatic, so two prismatic, one helical. It depends upon the design of the robot and the application, and so this is one classification as well. Then there is a requirement of then there is another classification of closed chains and open chain robots. This was an example of open chain robot because the end effector or the number 4 joint or this XY is free to rotate. It has no constraints, right? It will go wherever all of these theta takes it, but it is independent actually. Uh, uh, and uh, and then there is a category called closed chain robot. As I have shown here, this is called a delta robot. Now Now the application of delta robot is it generates a lot of force so that we can just lift up a few kgs of a few kgs, or depending upon the road we can lift a lot. The best example I would give you is, do you know what a space uh, emulator is? Anyone? Have you seen that movie Apollo 13? uh, Suppose if the astronauts are supposed to go to the space, or you might have heard a lot of buzz. There was a lot of buzz when SpaceX sent a few people to International Space Station. It made a lot of headlines, and obviously, if you are going to space, or if you are going to visit the ISS, you are required to undergo a lot of training in able to just survive the harsh environment. And sometimes the things can get out of control. Not sometimes, it gets out of control a lot of times. And so this there is a thing called space emulator. It just simulates or emulates what kind of atmosphere would be, or what kind of forces or would be applied in if you are sitting in a spacecraft. And to lift that or to move that in the required direction, these type of closed chain robots are used. This is a delta robot. I'm not sure if this one is used, but there is a thing called steward platform that is extensively used in the space emulators, and even in flight emulators as well. If you undergo pilot's training, this is used there. And the whole box, or where you are supposed to control it, all stands up on this one, or a combination of these. And the second one here is a mechanism base. Now, I would like to ask the attendees here, how many of you have a driver's license? Anyone who has a driver's license? Yeah. Can you please unmute yourself and introduce? Who raised the hand?
Meghavi.
Yeah, please go ahead and please introduce yourself once. I guess. So the whole point of the discussion was, if you were given a license test, assuming you have not cheated by paying 5,000 to the to get the license, but if you have been through those tests, you must have encountered one problem at the beginning, that is parallel parking. And I feel that was the most difficult when I was appearing for the test. So how do you do that? First of all, you just you move ahead, then you turn your car in particular direction, and then you take this curve until it fits perfectly. So like that is a bit complicated process, and it's very hard to perfect that. So imagine if you were to just travel to the just side of it, and then the car just slides in right away. You don't have to do all of these things. It's turning and reverse gear. It just slides. It moves like that. You might have seen that Apple concept cars as well, where the wheels they just turn and it goes inside. So this is one of these things. This is a mechanism base, and it's the best part of it is it slides. It doesn't. We are not required to control to control it in a way like we control the car. The wheels just slide left or right. It can also move forward, backwards, and it is used extensively in warehouses where we need to increase efficiency without procuring any additional hardware. And this is a KUKA U-bot. This is extremely famous in the robotics community, and this is something that we at Creators we are going to be building once uh, people are present in online in full capacity. And you might have noticed I have mentioned here the term holonomic. So that is a very complex concept within itself. But only brief introduction I would like to give is what actually a holonomic and difference between holonomic and non-holonomic is. In holonomic, there are no constraints, and in non-holonomic, the constraints on velocity do not integrate to the constraints on the displacement. Now that is a lot to take in, and I wouldn't say anything more than that. But you can just remember in terms of this, if it's holonomic, then it does something what we do not expect at all. Like it slides left, right. I mean, it's very interesting and it's very surprising to see this. I mean, if I would have had it, I would have cleared my license in the first time, but it's all gone. So we'll move ahead. Now, now we are going to be venturing into the next section, that is visualization and simulation in robotics. So, in everyday usage, both the terms visualization and simulation are used interchangeably, but in robotics, there is a fine line between these two. So, what do I mean when I say visualization? Visualizing a robot means to quantify and model the appearances and physical properties of the robot. We can specify the values of mass and inertial distributions and also add virtual sensors that can be further used in simulation. So, visualization means that we are going to be preparing what the robot looks like, and if we were to touch it, what it would feel like. So, suppose if you were to touch uh, if you were to touch shape, then you can easily perceive it, like whether it's a cube or a sphere or a cylinder. And you can also, like if you were to lift it, you would feel that is it heavy or is it light, or what are its mass distributions, if it's perfectly distributed. You will get a sense or a feel of what the thing is. That is visualization. But and the second part is simulation. Simulation is the interaction of a robot in physics-based environment. So if we know what the robot looks like, what it feels like, then if we were to put it in any physical environment like the world we live in, which where there are a lot of forces, and there is gravity, drag, everything, friction. So how the robot would interact in the actual world is something that we do in simulation. Make sense? So, what is the need for visualization and simulation? So, simulation is one of the most important tools which is used in robotic development pipelines. So, let me tell you one great fact, that without simulation, the building of robot is not possible at all. No teams, even the best teams in the world, they would first simulate. They would first design the robot. They would visualize it. They would see how does it look, and then they would start the process of simulating, like how well does the robot perform in the simulation. Obviously it's not going to be as accurate as it will perform in the actual world, because the motors we use or the batteries we use or even the mechanical components we use are not perfect here also. But in simulation, we are not assuming they are perfect. The simulation gives us near good results, but what we will get in the by making the actual hardware will be quite different. Not quite different, but a few, there will be a little bit of difference. So, but simulation is the closest we can get to it. It helps to test our robotic algorithms without any hardware implementation at all. This reduces the cost of developing the products. So imagine if we, without this workshop, if we were directly met and we would be assembling this differential drive robot, and you have written a particular algorithm, but you don't know the constraints about how fast or how slow, how fast the the motor can move. And if you give a particular output and the robot and the motor tries to execute that output, and then there is a very good chance that the motor might get damaged, or the if the algorithm is not proper, the robot might crush into some of the obstacles and the sensors or the body parts might get damaged. I mean, there's a very high probability that this might happen, and this happens all the time. Even in simulation, the robot might not work as expected. So this is how you precisely develop your algorithms. You start with something and then you just keep on what improving them after every iteration, and then you get is a final and a precise implementation that consumes less memory, processes faster, and gives you the most accurate outputs. So it allows us to it allows us to like improve at every stage of our development. It also prevents our actuators from the damage that may arise from blundering algorithms, is something I just discussed. Every simulator passes the URDF of a robot, which cannot be developed without step-by-step visualization. So what the simulator does is it parses the URDF file, and visualizer actually does the same thing. So if we do not know, or if we are not sure that the robot actually looks and feels like what it's supposed to, and if we put in the simulator, we will get inaccurate results. So if we want to start a robust development process, then we first started by visualizing the robot, and then we put it into simulator, and then we start implementing in the actual hardware. So this is the actual pipeline that is followed by robotic teams across the world, even in academia and even in companies like KUKA. Obviously, then this all boils down to the individual departments, and something that we'll elaborate on in the next section.
Yeah, there is a query. What is URDF?
Now this robot is uh, so this is an example of something that we have been publicizing very extensively. This is something we are going to be making by the end of this workshop, and this is just a snippet of the code or an excerpt from that code. So this is this scary looking XML code. It translates into this beautiful robot. So this is something we are going to be doing, and I suggest you pay attention to all of this. So now, what are actually the constituents of a robot? So at its core, a robot is just a coordinated assembly of various mechanical and electronic subsystems. So what happens is there is a thing called closed loop systems. Uh, can anyone raise their hands if they are in their second or uh, if they are in the second year? How many of are in the third semester? Jill has a question about what is URDF. Jill, we are going to be discussing that in later parts, the last section, and it will be clear. So yeah, I can see a few hands. Uh, in electrical, I don't know about other branches, but what we are taught is a control system, and the closed loop means what there is a block diagrams. There is a process in which we continuously take feedback about what our actions did, and based on that we try to improve each and every time. So I give you a very trivial example, very trivial. Suppose you are driving a car, and you are um, at a normal speed, it's not a problem, and then you suddenly see that there is a person or a dog which is crossing the road, and you need to stop. So what happens during that short span of time? Uh, so what actually happens is, first you are controlling the velocity of the car. You have your foot on the pedal, and if you and you can push it, and that way you control the speed of your car. You are perceiving the world around you by your eyes. Obviously, uh, you are just seeing the road that lies in front of you. You can, if you see any obstacle, or if you see someone is crossing the road, you will see, and then you will try to slow down the car in just enough time that you don't hit the person. And that is exactly what happens in an actual control system. You see, the sensor perceives the output and sends the signal to the controller, and then the controller gives out a control signal that controls the process. Now I'm sorry that got a bit complicated, But coming back to our example, the sensor here is your eyes. Your eyes is generating a signal that there is an obstacle, and it is generating an image, and that image is being transferred to your brain, and then your brain thinks that oh, there is an obstacle or there is a person crossing the road, and then we need to slow down the car, and the brain gives you your legs, in this case, a signal that you need to slow down the car, and then you actually do it. And this process, this is what exactly happens in a robot. Here, instead of obstacle avoidance, it can be any other thing. It can be literally any other thing. If we need to move to a particular location, if we need to generate particular torque, it can be anything. Uh, this process repeats over a sampling interval, like in 1 second, or if we are working with high frequency robotics, then this whole thing happens within just a few milliseconds. But in order to execute that, you require faster processors, and which is something we'll elaborate in just the next section. So first is a motion planner. It generates the theta. The theta is something I discussed in the joint link diagram. It's just a vector, or I can say an aggregate of all the individual joint movements, and it generates like how much the joints need to move. Then that signal, that theta, is passed to the each and individual actuators. In this case, we'll be using motors, and the reason why we use motors is something where I will elaborate later upon. Uh, but the thing that controls the motor is a microcontroller, and I'm sure you have tinkered around with Arduino. You might have controlled a few servo motors or stepper motors, or a basic DC motor as well. So you know that how a controller or a microcontroller generates a voltage or current that is passed to the motor, and the motor does the required. It rotates by a certain angle or at certain velocity. Then we have some sensors which are attached to that motor or that actuator or to the robot, or we have cameras as well that checks or tries to abstract how much there has been change in the state of the robot. By state of the robot, I mean how much a robot has moved, how much it has rotated, or any other thing that is interested, or which is desired to control. So sensors do this, and they pass the data or the signal to the motion planner, and this forms a closed loop system, and this continues over and over and over and over again. So just imagine what is happening. If even the robot has to move by 1 degree, a lot of calculations go in the background to be able to make sure that the robot has moved by 1 degree only. Even extremely sure if we give the command for the robot to 1 degree and it moves by 1 degree, because our actuators are not perfect at all. In the real world, they aren't perfect. They are not precise as well. So, like I said, a robot is just a coordinated assembly of various mechanical and electronic subsystems. So now I'll go into depth about what these mechanical and electronic components are. So, you you need to understand the fact that the main thing that does the processing is obviously a processor. It can be a small computer like a Raspberry Pi or Jackson Nano, or two high-end processors, or embedded processors as well. They generate the signals, and the mechanical components are the ones that need to be actually controlled. The links need to be at particular place, the joints need to be at particular angles. So we'll just discuss what those mechanical components are. So the first is a chassis for wheel mobile robots. And now the chassis is something you are extremely familiar with. Your car, the car you drive has a chassis, and there are internal components in it. So the chassis always forms the main part of a wheel mobile robot at least, um, and that is a mechanical component that we need to design. It needs to have certain physical qualities. it needs to be strong, durable. But depending on upon the application, the qualities change, and that is something we need to keep in mind while the fabrication of the robot is being done. Second is the end effector. Now, end effector here is a very technical term. Obviously, we are making a robot. There are varying degrees of end effector. Suppose we use robots for automatic welding as well. We use it for pick and place. We use it for sorting of things. So there, depending upon the application, and end effector changes. So if we are using the robots for welding, then the end effector will be a welding torch. It you know the how but the actual welding process is. And for pick and place, it's the robotic hand. Like it reaches the particular position, then the end effector closes, the hands close, and it picks it up, and then it transfers to the required place, and it puts it down. So that is an end effector. This is both of these are extremely important while we are defining or designing a robot, or when we are fabricating the robot, and this requires precise mechanical calculations and modeling as well. For this, you might use CAD software or ANSYS or something. Then the third one here is the links. Like I said in the joint link diagram, link is something that is a part of an actual robot. Obviously, there needs to be some a mechanical interface between two joints, and these links need to be reliable. It needs to be able to withstand a particular amount of force, and might also it also provides a protection to the internal electronic components. If you were to open up a robot, you can see the chain of wires just going in and coming down. So the links provide this casing as well. Then there is the main thing, and then there are joints. Now, joint, as I said, is an intersection of two links. It needs to be it needs to have low friction. It needs to be light or heavy, depending upon the application as well, or depending how well the our motors can control that joint. So the joint is also a piece of work, and it's one of the, obviously not one of the most crucial component when it comes to designing a robotic arm. So that is, and then gears are used for to convert gears are used with the motors in order to generate a high level of torques. We can adjust the gear ratios and get the required torque what we want. And then the wheels, for wheeled mobile robots, obviously wheels can be a lot of, we can have normal wheels, and we can also have the mechanism wheels, the one which we discussed quite in detail in the first section. So depending upon the application, the wheels uh, are changed or generated. Then the second last one is the motor mountings. Obviously, we just cannot put motors anywhere. We need to design a specific mounting case which holds these motors together, and that is a very precise thing to design as well. Uh, Not to mention, there are a lot of patents being made in this area. Then there are enclosures, like I mentioned, in links. Even there are even when we are connecting those joints, we need to enclose them in particular casings so that they are not damaged by or influenced by the outside world. And when we are working in industries where there are varying levels of dust that even we cannot control, enclosures increase the lifespan of robot drastically. Now the main is the electronic subsystem. Now I might have not elaborated on the term what subsystem is. It's actually a group or a combination of similar elements That was a mechanical subsystem. This is the electronic subsystem. The first and the most important is a central processing unit. Now, central processing unit means it can be anything. It can be it essentially means microprocessor that is capable of performing a lot of computations at a very high frequency. For example, obviously, these processors are everywhere. You have one in your laptop, and obviously, your robot requires one as well. I mentioned the term Jetson Nano or Raspberry Pi. We can use either of them for our projects. But if we have a deeper knowledge of embedded systems, we can pick up any commercial or any piece of microprocessor that suits our needs, and we can develop our code and get started right away with it. Then the second one is electronic speed controllers. So in order to control the motors, we need to generate varying degrees of, we need to generate particular voltage or in some examples, a particular current. So electronic speed controllers are used in that way. They generate the exact amount of voltage and current that are required to control the motors, and they also ensure that none of the terminals of the motors get damaged in the process, and they provide a very robust connectivity as well. So using electronic speed controllers is something that you should invest your money and time in as well. And in the other implementation of an ESC is a microcontroller. You can directly connect your actuator to the microcontroller. Like I mentioned in previous slides, you must have tinkered around with Arduino and stuff. So here Arduino is not used as a processing unit. It's used as actually something that executes the signal that has been sent by the processing unit. Now, I'm sorry, I forgot to mention uh, why the central processing unit is extremely important. We use in robotics, we have a lot of algorithms that determine that you should make very crucial decisions. And some of them can be localization problems, like where the robot actually is, or a motion planning problem, like where the robot needs to go from now. uh, a brief intro to that one is robot perceives something, and then it tries to divide the whole area around it in form of grid cells, and then it selects which cell to go. So that is an extremely computation. There are a lot of computations that go to achieve this desired effect. And in this, if you have a powerful CPU, or then you can get very accurate outputs, and you can use your algorithms at very high frequencies as well. Then the third one is sensors. Now, sensors, like I mentioned in the first diagram, are an extremely crucial part of it, because this is what allows us to answer a lot of these questions, like where the robot actually is. And a lot of example of these sensors are first is a GPS sensor. Then then we have encoders. Uh, encoders are used to determine the speed of the robot, and when we know how much the speed or the other distance that the robot has traveled, we can integrate and we can answer to this question of where the robot actually is. um, then we have bumper sensor, like we it helps us to check if if the robot has not crashed into an obstacle. And so the robot we are going to be developing requires a bumper sensor, because it's based on what we call as a vacuum cleaner robots. And you can see the vacuum cleaner robots have become extremely famous in recent times, and this is one of the examples of sensors. Then the fourth one is a power system. Now, like I mentioned, all of these are a part of electronic subsystems, and all of these are active components, and this requires power to be able to do basically anything. So we require a series and parallel combination of batteries and a battery management system that monitors these batteries in just in case if there is any fault. So power. So that is all about the power system. And then the fifth one is the human machine interface. Now, uh, if you might have watched any videos about KUKA robots, they provide this tablet that allows you to control the position of the robot. You can move some things here. You can move. You can even have a joystick control that allows you to move the robot in any direction you want. So that is an example of human machine interface. It basically means that our how the humans are interacting with the machine. It can also be a control panel. It can be a few switches. It can even be an app by which we are controlling. ROS has good functionality to control the robots from web interface as well. So that is one of the cool examples of human machine interface. So now we are moving into the next segment, that is locomotion of wheeled robots. Now what we are going to be building is a differential drive robot, and there are a lot of other drives as well. And we are just going to be touching upon on what those drives are. We are not going to go into the depths about what this robot actually is, what this type of drives actually are. We are just going to be discussing one in the detail. The first is a differential drive. The second is car drive, and it is in terms is referred to as Ackermann steering. The third is synchronous drive. Synchronous drive is basically a combination of three wheels that are moving at the desired velocities or something. And the fourth one is XR 4000 drive. And the mechanism wheels is something we have discussed, which I have brought up a lot of times now. So this is what differential drive typically looks like. I understand these equations can be extremely overwhelming, but the good news is you don't have to remember these equations or note it down, at least as of now, because what we are going to do is just model this robot. This help when you need to control the robot. So what is the differential drive actually? As you can see, there are two wheels, uh, two independent wheels. When you take the example of a car, the two wheels are connected to each other. Both of the wheels are traveling at the same speed, but in some of the cases when you need to take a turn, uh, the speeds are different, and that is because of a mechanical component called a differential. Uh, but here, both of the wheels are independent of each other, which means that both of these wheels have their own set of separate motors, or like separate motor. So there are two motors in a differential drive robot. Obviously, if there is a manipulator that is attached on the top of it, then there can be some other motors as well. But primarily for a drive, we require two motors that control the speeds of the respective wheels. And while controlling the speed of the individual wheels, we control the speed of the robot and in the whole robot. But we refer to the whole robot as controlling the speed of a chassis. And I'll give you one example as well. So first, we'll just touch on to the technical details about what what these terms are. So first is an instantaneous radius of curvature, which simply means how much if we are supposed to rotate this robot around a particular point, how much will be the radius. Our car has huge amount of radius, so this type of drive has basically less radius of curvature. And now these points are not that important. These have been mentioned for your understanding. You can just have a look at these equations, like how the individual velocities of left wheel and right wheel influence the translational velocity of the chassis or the whole robot, and how this how the individual translational speeds of left and right wheel can also impact the rotational velocity of a robot as a whole. Now, this is extremely useful because the algorithms we developed directly control the speed of, directly give the output as V and omega, and on based on that V and omega, we try to control this V, left wheel and right wheel velocity, and this is how, um, and this happens over, this keeps on repeating over certain sampling interval, and that's how we get the robot to move in our desired location, or desired specification. Now, this is also a bit overwhelming as well, but this is something, if you are into modeling the robots and stuff, and if you want to develop autonomous algorithms, and this is these are the matrices you are looking for. We'll be sharing this PPT afterwards, so you can have a look at that time. So, since we have selected this drive, I would like to expand on the fact what are its advantages and disadvantages. So first advantage is it's very easy to control. I mean, there is no complex control strategy. So if you want to control a car, then we need to control the front, the orientation of the two wheels that lie in the front, and we need to adjust the speed accordingly. Here we need to only control two wheels, uh, and so the control strategy or the control that we might want to design becomes extremely simple. So that is one the biggest advantage of differential drive, and ease of implementation. So now this boils down to the hardware ease that we by just combining two motors and attaching two motors, we can very quickly and easily implement an example of differential drive. Then there is less number of wheels. Obviously, it requires only two wheels as opposed to 3 to 4 wheels, and there is a relatively less radius of curvature, which is something I mentioned in the beginning.
If any one of you have doubts till now, you can ask, or you can even drop in the chat section. Else we will proceed ahead.
Yeah, if anyone has a doubt, this is the right time to shoot it away. Because I can understand this things might be overwhelming, but once we get to the URDF part of it, things get interesting and much more clear than it has and then it has been.
The project part you will enjoy. Yeah.
So, so obviously there are a few disadvantages to the differential drive as well. So the first one is it might spin out of control if there is a fault in one of the motors that controls the wheels. So let me take you this first diagram. So suppose if you want your robot to move in a straight line, then it is extremely essential that the velocity of left and right wheel is exactly the same. If it is not same, then we will have a certain omega value, and the robot will start tilting to left or right. So if we try to implement this differential drive in hardware, and if the motors are not same, or they do not have the same rating, or if there is a fault in one of the motors, it will directly impact the way the robot moves, and then it will spin out of control as well. There is a very good possibility that happens. So that is a disadvantage, and the structure is unstable but can be eliminated using castaways. So obviously, you might have had this thought: why, how are we stabilizing the forces? Because there can be a few forces on the top and front and the back side, and the robot might keep oscillating, and it would lead to a very unpleasant user experience. So what we do in this case is we stabilize the robot by using caster wheels. If our and the caster wheels are added based upon the design of the robot. The robot that we are going to create is the one. which will have two caster wheels because our wheels are in just the center. So we need to stabilize the robot, and for that purpose, we'll be using caster wheels. And you will see how we are doing that. So these are the disadvantages. Now both of these are not are not big problems. If we are using perfect speed controllers, and if we are aware of the motor ratings, and if we have tested our equipments thoroughly, then there is a very less chance that either of this disadvantage would be a problem. So we can eliminate that by incorporating various good testing practices. So now we are proceeding to the main one of the main section is the robot operating system. Uh, One, if you read this term, robot operating system, you might get this thought that this is actually an operating system, but as a matter of fact, it is not. It actually works on top of an operating system. Uh, Over the years, it used to work on Linux exclusively, but now the developers are also rolling out a few versions that work on Windows and Mac as well. So those once those stable releases are in, we'll be able to use them on our Windows as well. But as of now, the version we are going to use has only support for Linux, and that's why we are going to be using the platform construct, which gives us a Linux virtual machine, and is something we'll be able to work on. So why should we use ROS? I mean, there are some alternatives for ROS, but at least for visualization simulation purpose, there are a lot of alternatives. But why do we have to use ROS only? So first of all, ROS is a middleware software framework used for creating robotic applications. ROS provides everything from designing a robot, from visualizing it to the algorithms that control it, the localization algorithms, the controller plugins. It has basically everything, and this is something I'll be listing down now. The first is a message passing interface. So this is an extremely convenient thing that ROS has done. Is like the two parts of the robot. If suppose I have one processor and I need to be able to talk to the motor, like I mentioned the fact that the motor has to move by a certain degree. So now how am I going to convey this message to the motor that it has to move by this particular degrees? So that is a message passing interface. The ROS provides that, and this is one of the first things that ROS did while it was released into, I guess, in 2010. That it provides a robust message passing interface, and that is something which is plug and play type of thing. We can take out if suppose we are passing messages to this particular motor, let's name it M1, and if we were to take out that motor and we were to put in another motor, we would there would be no problem in connectivity as well. So I'll expand upon this communication part in the upcoming slides. Now, second is hardware abstraction and low-level device control. Now, this is ironic. First of all, we are abstracting the hardware, and in just a few words, we are saying that we are also controlling the hardware as well. So I'll explain both of these terms now. So, what does hardware abstraction means? Uh, uh, if you have, has anyone here worked with a BLDC motor in Arduino? Anyone? BLDC motor or any form of motor, servo motor. It comes with that kit. If any one of you has worked, can you please unmute and speak up?
or if you have seen before.
Okay. So when you are writing the so when you're controlling a servo motor, the first thing you do is you instantiate a servo object. Like I forgot the syntax, but like instantiate that object to a particular Arduino port. You map that object to this particular port. That this port will generate the necessary voltage that will control the servo motor. So, but if you were to if you were to find the plugin, and if you were to open that plugin up, or that header file, you will see a lot of low level C code, like low level embedded code. And there are a lot of capital things and a lot of scary looking stuff, like there is an I2C thing, I2C line, then there is an SPI line, and there is a memory.h file. A lot of things are going on down there. So that is an abstraction. So what the developers of Arduino or that particular library did is they wrote all the low level boring code for us, and the only thing we need to do is to write servo.write, is to type the command servo.write, and the motor moves. Servo rotates by a particular angle. So that is what is called hardware abstraction. ROS has already a lot of this code pre-written for us, and the only thing we need to do is call it and implement it. As simple as that. So we need not waste our time writing that low level code, because obviously writing that low level code requires a lot of patience, and with a lot of and with Python becoming so popular nowadays, C is has the influence of C kind of goes down, but it somehow manages to stay afloat. So this is what a hardware abstraction is. But on the other side, low level device control, even though it provides hardware abstraction, we still have a lot of options to write this low level code and control the device. ROS provides plugins and libraries for that as well. Like if suppose we have a new motor or a new sensor that has no support, and if you want to write the package for it, or if you want to write the low level code for it, ROS provides us with that facilities as well. We have C, and we have various compilers that are inbuilt in the ROS, and we can just mention them and things would get done. And the third one is package management. Now, this is one of the best things that ROS can do, and this is something that we are going to be implementing ourselves as well. If suppose uh, I wrote a package, and if I'm giving it to Ria, oh, I can directly send her the package. She will clone that in her workspace and just build it, and she can use it right away. And I have also mentioned, I have also shared a link in the chat space, uh, where it is about our GitHub repository, something that we'll be working on. You can see that there is a command. Just a minute, I'll show. So as you can see, if you want to open this particular link, and you would see that we have created this whole repository. This is actually a ROS package. This is something you will clone using this commands. You have just copy and paste in your terminal. Obviously, don't do that in your Windows or Macintosh. Uh, we will use the Linux virtual machine, and you can launch all of these things by just copy and pasting. And this is something which will give you a hands-on overview as well. So this is a ROS package, and it's just because of this package management, you can very easily uh, download any package from the internet, and you can use it and integrate into your existing workspace very easily. So coming back to our presentation, uh, the fourth part is third-party library integration. Not only we can use the ROS inbuilt libraries, we can also use TensorFlow with ROS, use uh, OpenC with ROS, and a lot of, and you can use PyTorch. So you can name any libraries and we can use that, because ROS provides us a great Python interface, a great uh, a C++ interface as well. So we can use practically any libraries that Python, C++ supports. So that is a very crucial and very important point while using ROS, and this is something that developers enjoy. And the last second one is the language independence. Uh, the the main languages that we use while writing ROS code is Python, C++, low level C, and even an XML. So the code in that we are going to be writing for URDF is going to be in an XML kind of form, and the control part of it, if we were to write any control part of it, that will be in Python or in YAML in YAML. So that is one of the biggest advantages, because Python is something that everyone present here must know or must have worked with at any given time. So it is so it becomes extremely crucial for the people who just want to venture into this world of developing robots. And the last one is distributed computing. Now, like I mentioned, that the various robotic algorithms, they are very computational intensive. They require very depending upon the complexity of the models and the complexity of the algorithms, we require the uh, a high level of processors. But if even if we get the best hardware and our system is unable to is unable to make the complete use of it, then there is no sense developing these robots, right? This will just impact our cost, and we will not be able to achieve our desired targets. So this is where distributed computing comes in. ROS divides these computations into certain achievable targets and distributes them across all the cores, and hence we can get our output accurate and, but most important, extremely quickly. So this is one of the most commercial advantages that promotes startups to use ROS even in the final products. Uh, but established companies like KUKA, obviously they have their own packages, their own installations, and their own softwares. So they might or might not use it, but there are various commercial startups who have already begun implementing ROS. So this is a typical file system that is in the ROS. So at the top level, we have a Cat King workspace. Now we were not going to discuss how we create this workspace, because for this workshop it's not required. When we have a dedicated ROS workshop, we'll touch on all the commands, and that will be preferably offline. And in that Catering workspace, we have three folders. First is the Devil, Build, and SRC. So the build and the devel folders is something that we don't have to touch at any given time. If there is some small error that can be rectified by just making a few changes in the build or devel, then and then only we need to touch. Otherwise, all the things we are going to do is going to be in this SRC folder exclusively. And in that SRC, we have a set of packages. It can be infinite number of packages. uh, we have certain syntaxes by which we create package. The package is the most independent unit. We can extract this package, and we can upload it anywhere, and we can send it to anyone, and they will extract them back and then perform this build procedure that will be reflected in this folder. So this is good thing about packages. And inside this package, there is a standardized format of the folders that will be present in here. um, the ones that are extremely important to us is the launch one here. Our launch, this is the folder where all the launch files reside. It can be to launch various our it launches our C++ code, our Python code, and um, and all those things. Now this is something that is not extremely relevant to the scope of this presentation, But I like to just briefly touch upon what is meant by ROS communication, since I took a lot of time talking about what ROS communication actually is. So first is ROS topics. It's a way of asynchronous communication where the messages or the commands are being just published, and anyone can be on the receiving end of it, anyone. So it's asynchronous, which means that there is no synchronization between the sender and the receiver. The sender keeps on sending, and it's upon the receiver whether to take it or not. It's as simple as that. Then the second one is ROS services, which is a synchronous form of communication. Here, the receiver asks for it, and then only the sender sends it. So depending on applications, we can use both of them. But in certain conditions, we require a combination of both of them, and it's not possible for us to syntactically not possible for us to use either topics or services. And here ROS actions come in, which is a combination of both the paradigms. We can send and receive messages from both the ends and in both asynchronous and synchronous fashion. So now ROS launch files. Now this is something we are going to be using now when we will fire up our construct, and this is something we'll be typing in the terminal quite often. So these are our ROS launch files. The extension of these files is .launch. Uh, this is something that is just that it reflects in the ROS system, and the ROS will generate the necessary files that launches stuff up. We'll use it to launch our RVs. I have been talking a great deal about visualizing and simulating. So the software that is used to visualize is RVs, and the software that is used to simulate is Gazebo. So in order to launch either RVs or Gazebo, we require this ROS launch command, and it's extremely important for this workshop. The syntax here is ROS launch package name / file name. You can also see a good example. You can see here ROS launch. Uh, ROS launch is a command. Creators is the name of the package, and bring up.launch is the launch file. This is the way how we'll be launching. Suppose we have written the code about cylinder, and we want to see that if the cylinder has indeed spawned, or what is the dimensions, is it correctly integrating with the wheels. So this is how we'll be launching it up. And RBS is something that is uh, this is a very tiny software, and it spawns up quite quickly if you are operating it on a desktop, but we are operating in a virtual machine. And it's in one of those cloud warehouses of Amazon, so AWS. So it will take some time, few seconds to launch, but once if you launch once or twice, it won't be the issue anymore. So this was about launch. Now these are basic Linux commands. Uh, Now there are a lot of, obviously there is a list of commands we might use, but for our workshop, for this workshop, we only require these three commands. The first is mkdir. This is used to create a new directory or new folder. Obviously, if we use VS Code, we can just give a right click and create a new folder. But if you are writing in a terminal for the first time or any time, it's much more fun to write in a terminal than in VS Code. And I think that's a fact for me. So here we use mkdir. Then there is cd command. Cd helps us to navigate to any particular directory. Suppose we were to write cd and write. Uh, if we were to write cd and the directory, which is catkin ws/src, then we would directly navigate into this particular folder. In GUI based operating system, like in Windows, if we double, if suppose this is the file, and I double click into any of the things, then we get this particular directory. So either if we can click through it or if we write the command, it's one and the same thing. We navigate into that particular folder. And the last one is ls. It helps us to view whatever files or folders are there in that particular directory. That's uh, that's the job of ls command. So now this pretty much sums up our all the sections, and now we are moving on towards the coding part of the robot. Now this is something I would prefer to do after a break, because right now all of you might be quite saturated, and I am pretty much saturated myself. And this is something which will be much more fun, and we'll be tinkering with writing a few lines of code, and then we would have some sliders by which we'll be moving robot forwards and backwards and tilting it, orienting it. So this is going to be a fun section, and we'll be doing this after a break. Now we'll resume our the second part of this workshop. Now this is going to be a completely hands-on session. Uh, First of all, you need to create an account. Is the chat accessible to all of you? I have shared two links, and you have to open them in your browser. First is a GitHub link which we build off on, and the second one is the construct sim, which where we will do our simulations. So you need to open both of these links. Acknowledge once you have done, and if there are and if enough people have done it, then I'll proceed to the next step. I'll share my screen. Just a minute. So this is the link. The link will take you to this page. I'll just stop my sharing and I'll add. I'll enter my credentials and log in. Just a minute. So you can. Is my screen visible? First of all,
Yeah.
Yes.
and have enough people logged in. It's just you have to create an account. It's a normal procedure that you do everywhere. So here you have to be responsive and you have to be active so that I may know where to proceed next. Because we are going to be entering few lines of code, and then if there are errors, then I can troubleshoot them right away. Otherwise, it will become way too late and way too complex. So you have to be on pace with me. We are not going to do a lot of things as of now, but the beginning parts are going to be crucial. Otherwise, you may run into some very fatal errors that you might not be able to come out from. And those would be simply avoided by just following what I'm doing. So again, if you have logged in, you can just raise your hand. You don't need to even unmute yourself. You just need to raise your hands that you have completed the step. You can show this, show an emoji. So please do that. Since the workshop is a hands-on, so now this is the hands-on part of it. You are going to do exactly the way I'm doing it.
Yeah. Those who have logged into the link that was shared in the chat section, just raise your hand. Okay.
21.
Okay, so let us wait for 2 minutes so that everyone logs in. We will proceed at 2:28. Okay, we hope everyone has logged in. If any one of you is still left, you can raise your hand. We will wait. Okay, so let's proceed ahead.
So the first thing we have to do is uh, we have to click on this My ROS checks, and this will give us an option to create our own ROS check. A ROS check is nothing but the fancy name for a Linux virtual machine. Now, a thing or two about this platform is that it's hosted on AWS, and which is running some instances of Ubuntu or any Linux distribution, and these people have already installed ROS for us. Now, installing ROS is a very complicated process and it takes time. First of all, you have to dual boot your laptop. You have to install Ubuntu, which is preferred Ubuntu, alongside your original OS, can be Windows or Mac. So that is a tedious process. So these people have created an online version of it, and they give out a free tier where we can use 2 GB space. So I'll go ahead and create one. This is important. We have to select the ROS distro as ROS melodic. This is extremely important. Otherwise, we may run into some fatal errors. We have written our code and optimized it. Sorry, for ROS melodic only. So we select that one. You can name anything. I'll go ahead and type diff drive 3, because I've already created two of it. And here you can write anything. It's not an issue, and you can create. So now this will appear, and I'll go ahead and give it a run. This will launch instance, and here we have our all the required tools that we'll be needing for our simulation and visualization. So once the whole thing loads, I'll give you a brief overview of what the interface actually is. So by default, it's loading a lot of things. It's loading the graphical tools. It's loading Jupyter Notebook. Jupyter Notebook is something we won't be using, so I'll go ahead and close it. We'll be using ID, terminal, and Arcuate graphical tools, and also simulation, but we'll need that for later. So right now I'm closing it. So has everyone created it? Raise your hands if you have reached this step, because it was just nothing. We entered, we just selected ROS distribution as ROS melodic, and it and they and this was this was generated by default. So please give a reaction if you have done this. Okay, so now what we have to do is, now it's time that we will clone this repository into our workspace. So before doing that, I would just like to brush up a few things from this PPT. Uh, like I mentioned here, we have a Catkin workspace. So this workspace is there is a workspace, and our whole of the code or everything we do should be within that workspace and workspace only. So already these people have given us, they have created 5 workspaces by default, and and this was all created by default. Only the only thing we had to do is we had to add our packages, we had to build them, and we would be more than good to go. So the first thing I'll be doing is I have given this README file, and it has got all of the and it gives you more than enough information to navigate your way around the repository. So First, these are all the 5 steps that will be required for the installation. And we have this very convenient option that we can select, we can copy the code by just a click of a button, and it gets copied to our terminal. And the way we paste things in the Linux terminal is we use Control Shift V. But in that way, it executes the command also, so it's not a problem. So the first command was cd catkin workspace slash src. So we have this workspace catkin underscore ws, and that workspace has a src folder already in it. This is a standard ROS workspace, and so we have things by default. And since we have already worked this while preparing for the presentation, so this is something you'll find consistent across all. Now we are going to do is we are going to uh, fetch all of these files and folders and install them into this src directory. Like I said, this is a package and all the package reside inside the src folder. It is a ROS rule, it's a compulsion. So I'll go ahead and copy this code and I paste it. So now it has cloned into the repository which whose name was Caritas itself, and all the objects have been fetched. And as you can see, we have a lot of we have the whole thing inside in it, this package. But our task is not over. We have the repository, but ROS still doesn't know that there a package has been installed. It needs to be invoked. It needs to be said that there is a package. Now you have to build it. Now you have to generate the low level executable code for it, right? Because that was the hardware abstraction part of it. Like we don't have to write the low level code, ROS does it itself. So this is one of those things. So in order to do that, we need to navigate to uh, the workspace level. We need to navigate to this cat. We need to move one level up. So what the command is cd dot dot. So now we are in the workspace, and now we will give this following command: catkin make. This initiates a build process. And as you can see, our packages, this Kratos was now the catkin make command searched that if there was a new package that has been added. It found that the Kratos is the new package that has been added, and now it has been built. The files have been built into some executable code, and that is present in the build folder. Like I said, this is something we do not touch. See, this is the build folder and devil. We do not modify or touch these folders. So this has already happened. But the rule of the thumb, whenever you use ROS, whenever you have made any changes in your code, you have to give this catkin make and this source. This does nothing. It just it solves a lot of your problems. So feel free to, if you're working with ROS, just feel free to give this commands right and left. So, and as you can see, this command has been executed. So now we are more than ready to work things. But for one example, I would launch one of the URDF that we'll be building today. So I will go ahead and now I have given the command, but I need to open the graphical tools as well, because this is where this robot will appear, or always the software that will appear. So we'll be waiting for it because it's going to fetch from some virtual machine, and as you can see, it's here. I'll just go ahead and minimize them, and you can comfortably see that this is exactly something what we are going to build. And in order to terminate any process, all we have to do is give a control C. I think this is standard. This is a standard in Windows as well. I don't know if it's a standard in Mac, but in Windows it is. So this is a very handy way of uh, terminating any process. So now we have seen the visualization as well. Now we'll just go ahead and glance the code. Now since there are less people and there is a less response, I would just go ahead and explain the contents of the URDF file. I drag it here. So this is something which we would have completed, but there are less people, so I just go ahead and explain this one. This is the exact thing that we are going to build. I just put it here for your reference because see this sometimes you would forget the syntaxes, and we have designed the launch files in a way that certain parameters should not be changed here. So just for the sake of reference, we have put this here, and all we have to do is study line by line and write the code here. No. So this is what a typical URDF file looks like. What I'll just go. I'll just conclude this one very shortly. So what is a URDF? URDF stands for Unified Robotics Description Format, and it's an XML specification. I mean, it uses the same format that XML is, and uh, uh, and it's an industry standard for prototyping or modeling robots, like we're going to do now. But the thing about URDF is it's extensively used with ROS, and ROS has complete support for URDF in such a way that ROS has its own form of macro. Uh, that is called Chacro. It's pronounced as Chacro. That is XACRO. The thing is, when you write this type of code, it becomes extremely repetitive. So if suppose I have written one code and I need to create four robots for it, instead of copy pasting, I can just give some placeholders using Jacro, and I can specify. Uh, I can specify the macro for it in all the launch files, and I would say get those things done. So it's it saves a lot of repetitiveness and a lot of time while writing the code, and also it has some other advantages as well, which will not go into depth as of now. So this is a typical structure of URDF. Now this is extremely important while writing the URDF code. We have one main link, and we can have only one main link. And if there is there cannot be like two independent links that are not connected with each other. There has to be one link, and it has to be connected with other links in form of with joins, obviously. So I explain the API for it, how we connect two links together in URDF and preceded, and those links are connected by its other subordinates. So it forms a tree-like structure, like in any XML, it forms a tree-like structure. So that's pretty much it about URDF. Now we'll just examine the code for it. So uh, so first of all, we need to create a dummy base. Dummy base. The only reason for creating a dummy base is it's specified in our base that the main element or the core element of the robot should not have any physical or visual properties. It just needs to be a plain thing. So just and does not cause any big errors. It just raises an exception. So in order to avoid that, we use this form standard. It's not a big issue. However, The main code starts here. Uh, I first explain this link tag. So obviously, like in any scripting language, there is a starting tag and there is an ending tag, and same is and link. So for this one, it's a link tag. A link has three attributes: visual, collision, and inertial. Now, this all of these three attributes are at the same level. That means like link has three components: visual, collision, and visual is not a subordinate of sorry, collision is not a subordinate of visual, nor is inertial. All of them are at the same level. So now we'll examine what all these tags or these properties mean. First of all, visual. Visual means how does that particular component look like. Uh, so for this, we had modeled it previously in form of cylinder, but in order to but as you have seen in the RVish, it doesn't look like a cylinder at all. It has a very complicated and actually a very beautiful shape. So that is done with the help of meshes. This mesh, like what we did was we modeled a particular robot in software. Then we extract a mesh file out of it. That file has an extension .da, and we insert that mesh file and the related images in this meshes folder. So when we write this particular line of code, the this particular file is reference. That's it. And I'm sorry, I forgot to mention the fact that each visual is also has a geometry attribute, like what is the geometry of the particular component. So in this example, first it was cylinder, but we removed it and instead we made it as a complex mesh network. Then it has the visual has another attribute called origin. That means this part about how does the robot looks, what is the position of that robot, or what are its coordinates in 6 degrees of freedom. That is XYZ and roll, and RPY stands for roll, pitch, yaw. Roll is the rotation about x-axis, pitch is y-axis, and yaw is about z-axis. So when we are controlling our differential drive robot, we consider it we have to control x, y, and yaw. That's just an out of bounds information. Now second attribute is collision. Collision means what if you were to touch the robot or a robot were to collide with you, then how would it feel like? The physical feel of the robot is its collision, and it has also an attribute geometry. Now here we are defining the length and the radius. We are defining it as a cylinder. And now there is one particular reason why we have chosen a complex shape for visual and a simple shape for collision is because when we are going to when we will simulate a robot, uh, how the way we determine a collision is through calculations, obviously. Like if the distance between the two centers is less than the radius or the length, half of the length of diagonal, or one of the standard things, it becomes extremely difficult when the shapes are very complex. So in order to make these calculations much easier, we model it as a normal shape, as a standard shape. And in RVs or in any or gazebo, there are only three standard shapes. First is a cylinder, second is a cube, and third is a sphere. So everything we make must be a combination of one of these three basic shapes. Then even this collision has an attribute called origin. Now it is preferred that most of the times the origin of visual and origin of collision must be same. All the coordinates must be same because or they are just sometimes made different uh, because it won't matter. It won't cause a problem in simulating. But because in simulating, the collision plays a much important collision and inertial plays an extremely important role rather than visual. Visual is just for looking. Then the third one is the inertial tag. The inertial tag defines the physical properties of the robot. For example, its origin, like first of all, it's mass, that what will be the mass of that particular element. Then the second is the inertial distribution. You might have shared in 12th 11th mechanics, I guess, what is the inertias of some shapes. So that calculation is a bit complex one. So how we obtain these numbers is basic coordinate geometry and some very extremely complicated calculations. So I will not go into the depth at all. Well, the only thing we are going to do is we are going to understand the syntaxes, and rest is on each one of you to design the way you like it. So this is like visual and collision. This tag also has origin, but the difference is mass and inertia. And this concludes our explanation of one link tag. So now we have two independent links. There is a one dummy base which does not require anything, and there is one base link. So now we need to join both of these together via joints. So now this is how we define a joint. So we specify joint name equals base joint. It has now you have to be very extremely careful by naming these joints. It's good if you follow some conventions like using an underscore, because it becomes very easy to copy and paste these names, and it has to be consistent because the same joints are the names we are going to be using while controlling the robot. Our controllers take these joints as input and perform, and rest is the internal workings of the system, which I will not get into. The type of joint is fixed, that this is a dummy base and this is a joint itself, this is a base itself. So there doesn't need to be any movement between those two, hence this is fixed. And the origin we can select, like how where do these joints fit, or how what will be the point where these joints will meet, these links will meet. So this is that value, and the most important one is which specify which is the parent link and which is the child link. So yeah, the parent link, as I mentioned, is dummy base because uh, it's standard and it's a good practice, and the child link is the base link, this one. You can see we have also given this comments before the start of every element, so that you can know which element this is or which joint it is. Then so now we have a basic understanding of links and joints, how we implement them in URDF. Second is now we have left. Now we will just we'll just examine the wheels, how we have modeled them. Obviously, a wheel is a cylinder with a radius and a little bit of length, and this is the way we have modeled this. And we also have a mesh file for it, which shows how does the wheel look. Here we have also, like I said, we have modeled the collision as a very extremely simple one, so that the calculations become very easy, and it also has its own mass and inertial distributions, because that will be required while simulating them. So now comes the most important part, that is how do we connect the wheels to the base link. So now I want you to pay the attention that we will name the joint as wheel left joint. It's upon you, but you have to be consistent with your notations. The type here is continuous. In the beginning of the workshop, I mentioned revolute joint, but here we also have an option of revolute joint, but then we have to place constraints like in the limits as like 10 raised to 6 and to 10 minus 10 raised to 6. So and then that's just bad coding practice. We have an option of continuous joint, so we'll go ahead and use it. We'll specify the parent link, that is the base link, and a child link, that is the wheel left link. And we'll also specify where and how does these fields connect to the base. So the origin, the y coordinate, as you can see here, we have a dollar sign and a pair of braces, and inside that is an expression. Now this is a good way. If you do not want to calculate, you can just simply put it in this placeholder. It will perform the calculations by itself and put this standard value. The URDF parser will do this all by itself, and you need not get into uh, the waste of time by calculating by making these calculations. And the most important part is the role. The value of a role is being given as minus 1.571. So this is actually minus pi by 2. If you 3.14 divided by 2 is 1.571. So if you write a cylinder, it spawns in RWAs uh, as like a in this way. But since it is a wheel, it needs to be rotated by or along the x-axis by 90 degrees. So if you rotate it down or up, it's one and the same. So this is how we will rotate the wheels around x-axis, and we will get a standing one on which our robot can move. And that's the exactly the same thing we do with the right wheel here. We connect it with the base, and we give minus 0.23 by 2, and row is the same. So now the work of moving the robot is done. Now, since I mentioned in one of the disadvantages that the differential drive has is not stable mechanically, so it requires some caster wheels. So now we will go ahead and just model those caster wheels. They are going to be exactly same as the wheels. The only difference between them is first of all their position. The wheels are placed left and right. This will be placed front and back. Hence, we will stabilize the structure. And the second point is that the joints are fixed. We do not want our caster wheels to move. They are just there for support, as simple as that. So the joint here is fixed. So this is the same thing that we do with our back caster joint, and this kind of concludes our URDF of URDF of our Kratos robot. So if anyone has any questions, please shoot them right away. Because now I will teach you how to launch these files or any file for that matter. Anyone has any doubt in the code? Okay, so I'll go ahead and launch this once more, but this time I'm going to write the code. So the code is ROS launch. Now we'll write the package name. The name of the package was Kratos, and we are going to be launching the file. This one. See, the launch has 3 launch files. It has a launch file for launch for displaying the first robot that we were actually going to code hands-on. This is the launch file for the robot I just explained. It's just the same. Instead of Kratos, it's Kratos 2, and then makes no difference. But this one is our simulation launch file. This is for visualization, but this is exactly for simulation. Here we'll be simulating, and we'll also be moving it around in the world. So first we'll launch this one, and then after that we'll do the simulation one. So we go ahead and write the command. So now the file has been launched, and we'll see what appears. See, as you can see, RWS, and our model has successfully appeared. You can move around, you can see, you can also examine stuff from here. For example, uh, so like if we are making this as a fixed frame, then this it will respond in that manner. I just go ahead and make this dummy base because it's by default. Uh, you can this actually a bit laggy, but if you have a dual boot, you can tinker around with it. This package will work just fine in your local machine as well. It has been tested for that. Now I'll just go ahead and disconnect in this process, and I will launch the simulation. So for launching the simulation, we need to actually open Gazebo, and it will and once I will write the command, it will actually launch. So it will spawn here in a couple of seconds. So as you can see, our model has spawned, and now I will try to move it ahead or rotate it, tinker around with it. So these are the sliders. I mentioned the term topics, services, and actions. So what this is doing is it's just publishing velocities, that is forward and backward velocity, rotational velocity of the chassis, and publishing it onto some topics. And because of that, the robot moves. So I is just put the slider and the robot moves forward. Then I give it a turn, and it gets a rotational velocity, and it makes a turn. I'll put both of them again back to 0, and it stops after some time, and just now I just give a negative velocity and some negative rotational velocity as well, and make it stop. So this is pretty much how we simulate stuff. If it was a normal Ubuntu, then uh, you would get a better experience tinkering around with these things. But since this is all working on a virtual machine, we have some constraints for this online workshop. So pretty much that's it. A word that we are going to be making this same thing, same robot in hardware. So not in maybe in the next workshop or the coming workshops. So you need to you can practice this whole code. The whole package is with you. The repository link, you might have cloned it, so you can just read the file and you can mess around with it as per liking. So that's pretty much from my side. Yeah, you can.
Okay. So yeah, we hope that you got to learn about many different concepts, many different insights of the project. We will be coming with the similar workshops for the next month. So stay tuned for that. And the source code and the presentation file, we will share it in the group. So if you need for future, you can have it. And if you have any doubts or any queries, feel free to message in the group. We will help you out. So thank you for coming. We hope to see you in our next workshops.